Okay. Good morning, friends, and welcome back to Heat Transfer. It's a very rainy morning at IIT Kharagpur. I hope all of you are doing well at your respective places. So in the last class, we decided to start radiation heat transfer. And we started that. We talked about the basic concepts of radiation. And then we started on the emission characteristics of a surface. Okay. So what we are doing right now is we are defining certain terms. Okay, we defined what is a black surface. Okay, and then we started looking at different properties. The two properties that we had defined in the last class was total hemispherical emissive power and the total hemispherical emissivity. Okay. So let me get started with sharing the screen and continue from where we left off. So let us now define the third term. Definition 3. The definition 3, we talked about what we said, total hemispherical emissive power, right, in definition 1. So what we would like to do is, we would now like to distinguish the emission characteristics by wavelength. Okay, so the next term that we are going to define is called monochromatic. Instead of total, it is monochromatic hemispherical emissive power. Now, what do I mean by this? Okay, we write it as E sub lambda. Okay. Now, what do I mean by this? It is not easy. There is no like closed form concise definition. It's a very loose definition. Let me write that. What we say is, it's a very amateurish definition. It is that quantity which, when integrated over all wavelengths, gives the total hemispherical emissive power. Okay, so what I'm trying to say is E is integral 0 to infinity E lambda d lambda. Or E lambda is dE d lambda. Okay, maybe it will become a little clear if I think we have drawn this before. We'll draw it again now. Remember what we said before, that emissive power per unit area at a given wavelength. We had drawn that before, right? And we said that it looks something like this. Right? And we said that this is most interesting. Most of the radiation happens between 0.1 and 10, right? So now we will define this term as E lambda. So what we were actually plotting at that time when we were writing some text on the y-axis, that was essentially E lambda. What would be the units? Watt per meter squared. You can say per meter cube, but typically what we write is watt per meter squared micrometers. Okay, that's typically used because, you know, if you try to express wavelength in meters, that would be like too many zeros after the decimal point. Okay. So what it also means is this area under the curve is actually your total emissive power, total hemispherical emissive power, E. Okay. So monochromatic hemispherical emissive power for a black surface, therefore, is denoted by E B lambda. Okay. So similar to definition 2, therefore, now we will write a definition 4, which is called monochromatic hemispherical emissivity. And denoted by epsilon lambda. Okay. What is the definition? Ratio of the monochromatic hemispherical emissive power at a given wavelength to that of black body at the same wavelength. Okay. Ratio of E lambda to EB lambda at the same temperature, definitely, and wavelength. So epsilon lambda therefore is E lambda by EB lambda. Okay. So how do I graphically represent this? This is how it is. Let me plot the same thing over and over again. Lambda, this is E lambda. Okay. So for a black surface, let us say this is how it is. And for the real surface at the same temperature, let us say this is how it goes. Okay. So if I take a certain lambda value here, now both of them are at the same temperature. Okay, that is very important. This is also at T. Let's say T star. This is also at T star. Very important. Okay. So this is E lambda, and this is EB lambda. Okay. So this curve was for a black surface, and this curve was for a real surface. Okay, so similarly what it means is this is the emissivity at that particular wavelength. Okay, we can also say right now that epsilon lambda lies between 0 and 1. Okay, so that brings me, definition 5, which is called the gray surface. Okay. What do I mean by this? Let us say I now start plotting the monochromatic emissivity as a function of lambda. So what do I have to do? I have to take every point, I mean this value of epsilon at every point, every value of lambda, and plot it. And I may see that the curve varies something like this. Okay. So what we do is, this is an engineering approximation. And it says that if we take just the average, okay, something got stuck in my throat today. So if we take this average value, then it's called a gray surface approximation. So engineers average epsilon lambda to a mean value over the entire range of lambda. So this is called the gray. The gray is spelled both ways, G-R-E-Y and G-R-A-Y. This is called the gray surface approximation. Okay, so in other words, what is a gray surface? It says that gray surface is one such surface where it has the same value of monochromatic emissivity across the entire or across all values of lambda or wavelength. Okay, it's an approximation because emissivity or monochromatic emissivity is going to be a function of wavelength. Okay, now can we use this? So that is what, can we use this in every place? No, because, and we will do some problems later which will show you that, you know, now people who work on these surfaces, radiation heat transfer, they have come up with certain surface coatings. Okay, so these surface coatings have selective power. They can have, you know, emissivity values which are extremely different over certain values of wavelength. So these are engineered surfaces. So therefore, let us say from, I don't know, so let's say 0.1 to 0.5 microns. The emissivity is 0. Let's say 0.5 to 5, it turns out to emissivity is around 0.5. And then 5 to 10 microns or 5 microns then to infinity, it is 1. Okay, it is possible. It is possible to create such surfaces. I mean, the numbers I told you are something that I just made up, but it is possible to have engineered surfaces which have very different values, extreme varied values of emissivity over certain wavelengths. So in such a case, if you want to average it out and make a gray body approximation, then you cannot do that. It's not going to be a good approximation. Okay. But otherwise, for many other surfaces, most of the surfaces that we look into around us, etc., which are not those specialized engineered surfaces, the gray surface approximation works very well. Okay. So what are the 5 definitions we have come up with? Let us write them down. Total hemispherical emissive power. Total hemispherical emissivity. Monochromatic hemispherical emissive power monochromatic hemispherical emissivity, and finally gray surface. These are the 5 things that we have defined. Okay, please, I would request you now, I'll give you 30 to 45 seconds. Please go through these 5 definitions again in your notes and make sure, convince yourself that you have understood what each of these mean. And if you have any questions, please feel free to ask. Okay. I am also scrolling. Yes.
Yeah, sir. So, like in definition 1 and 2, we have that physical significance that it is radiant flux. Do we have something for monochromatic um, power?
Yeah, that is also radiant flux, but it is the radiant flux at a certain wavelength. Okay. It is difficult to visualize something or feel something. Let us say you are having a packet of energy coming out. If you had a way to differentiate at what wavelengths they are coming out, then that is monochromatic emissivity. Sorry, monochromatic emissive power. Okay, so you have to be a little imaginative, and that's why I say, uh, I mean, I used to have some physicists as my colleagues in my very early professional life, and they used to really look down on us. And they would say, you guys don't understand, so we have made all these approximations for you. So that's how it is. I mean, if you go to the Western world, people who are into pure sciences, they are held at a much higher pedestal compared to us. In our country, it's a little different. The perception is a little different. Primarily because I think engineering profession fetches you more jobs than pure science. But I think in terms of intellectual or academic merit, pure science have always been ahead of us. They can imagine situations which we cannot. Of course, I'm not undermining engineers, because engineers actually make the things which we use. Okay, it's not just enough to be hypothesizing and be imaginative and innovative in terms of theory. It's the engineers who make these selective surfaces. Okay. So now these are the 5 definitions. Now what we do is this total hemispherical emissive power. I mean, these are too long, right? So therefore, what people have done is they many a times, or most of the times I would say, dropped these terms. Okay. Okay. So if somebody says the emissive power, it means total hemispherical emissive power. Similarly, emissivity, if somebody says emissivity of the surface is 0.2, it means total hemispherical emissivity. Okay. Similarly, so it means that it is summed over all wavelengths, it is summed over all directions. Similarly, monochromatic, hemispherical, emissive power and emissivity, again, we drop these terms. Okay. So therefore, when we say emissive power, once again, it means total hemispherical emissive power. When we say monochromatic emissive power, it means monochromatic hemispherical emissive power across all directions. Okay. The other thing I would say is, many a times, the word monochromatic is also, or is not also, is replaced by the word spectral. Okay. So people may say the spectral emissive power at whatever 500 microns, at wavelength of 500 microns is so much. Is X watt per meter squared per micron. Okay, so it means monochromatic. So these spectral and monochromatic are used interchangeably. Okay, all right. Oh man, you can hear the dogs around us have gone crazy in this weather. It's again started raining. Really feel for them. I have given shelter to a couple, but most of them, it's very, very tough life for them. Okay, a small exercise, and this is for you to do at home. It is very easy actually. Show that epsilon, which is emissivity, total hemispherical emissivity, is 0 to infinity epsilon lambda EB lambda d lambda over EB. I think this is by definition, okay. All right. So now that we have equipped with ourselves with the definitions, we know what are the emission characteristics. Emission characteristics. Remember, we started saying that any surface, by virtue of being at a temperature which is higher than absolute zero, is going to emit thermal radiation. And how do we quantify that amount of radiant heat flux or thermal radiation? We have defined certain quantities. Okay. Now, after this definition, we are going to talk about laws of blackbody radiation. I mean, again, they're called laws of blackbody radiation. Traditionally, they're called so. We cannot do much, but as I said, that it is the radiation characteristics of a black surface. Okay. There are 3 such laws, and you have heard about all of them. Planck's law, Wien's law, which is also called Wien's displacement law, and number 3 is Stefan Boltzmann law, or is B law. Each of them have their own functions. Okay. Planck's law, it gives us an expression for E lambda. Sorry, EB lambda. These are all black body, so EB lambda. So what is the monochromatic hemispherical emissive power of a black surface at a given temperature? That is given by Planck's law. Okay. And I believe even before we look at that law, that expression, you can guess that EB lambda is going to be a function of lambda, definitely, and the temperature. Wien's law, it says that at what value of lambda is the maximum value of EB lambda obtained. Okay, and Stefan Boltzmann law, it gives an expression for EB, the total hemispherical emissive power of a black body. And as we said, we normally don't drop those first 2 terms. So Stefan Boltzmann law gives the emissive power of a black body or a black surface. Okay, so these are the three laws, all related to emission characteristics. Okay, so let us take each of them one by one, starting with Planck's law. As we said, it gives us an expression, allows us to calculate the monochromatic emissive power of a black surface. Okay. Now, what is the law? Planck's law of blackbody radiation is EB lambda, monochromatic emissive power of a black surface. And that is given by this expression. Sorry. In the numerator, you have 2 pi C1. And in the denominator, you have lambda to the power 5 E C2 by lambda T minus 1. Okay. Lambda is the wavelength, T is the surface temperature in absolute scale. Keep that in mind. So true, as we could guess, that this emissive power is going to depend on lambda and T, the emissive power of a black surface. So this is the expression. So it gives you remember that curve that we were drawing, this is the expression for that. Okay. So constants, constants C1 and C2 come from experimental data. Okay. So C1 is 0.596 into 10 to the power minus 16 watts per meter squared, and C2 is 0.014387 meter Kelvin. Okay, clear? I think this will be meter to the power 4, isn't it? No, right, this is correct. Okay. Yes, this is the mistake I was doing. Okay, watt meter squared. That's why the definitions I wrote it wrongly, incorrectly. So numerator you have watt meter squared, in the denominator lambda to the power 5. So finally, EB lambda has meter cubed or length cubed at the denominator. Okay, so dimensionally it is correct. Now, nature of this law comes from certain EM considerations, okay, electromagnetic considerations, which I mean, honestly, I also don't know and not required for this course. But of course, if you, for higher courses in radiation heat transfer, yes, you need to know the physics of electromagnetic radiation. So Planck's law, extremely important, tells us what is the monochromatic emissive power at a given wavelength and temperature. Okay, so from here we can write, therefore, for a non-black surface, E lambda is going to be what? Epsilon lambda times 2 pi C1 divided by lambda to the power 5 e to the power C2 by lambda t minus 1. Okay. Now the thing is that this expression of EB lambda if we start plotting, okay, this is the nature of the curve. We have seen this before. Okay. If we plot it for another temperature, sorry, this is how it looks. If you plotted some other temperature, this is how it looks. Okay, so if we increase the temperature, Planck's law will give you curves like this. So if you observe, what you see is, number one, the shape of the curves. Remember the similarity analysis that we did, similar to that. Shape of the curves are similar in the sense that lambda goes to a maximum value and then tapers down. Okay. As temperature increases, curve shifts to higher values. So which means that as your temperature goes up, the radiation given out, emitted, is also higher. And number three, lambda at which EB lambda is maximum shifts to the left as temperature increases. These are three observations that we can see, right? If I plot this, the last one especially, this is how it is, right? It is shifting to the left, this peak. Does everybody agree? Or are there any questions? Right. So three observations. We have just plotted that Planck's law expression as a function of lambda for different values of t. And what we are seeing is First of all, the nature of the curve is something that we have plotted several times before. But as I keep on varying the value of t, we see that the monochromatic emissive power is higher if the temperature goes up at a given wavelength. And secondly, the wavelength at which the monochromatic emissive power is maximum shifts to the left as temperature goes up. So now can we try to find out what the location of this maximum? Okay. Location of the peak. Or maxima. So what will you do? We will call our good friend differential calculus and say that d lambda equal to 0. Okay. So I'm not going to go through the derivation because the derivation to a certain extent, I mean, if you take like, see, EB lambda is a complex expression. If you take that C2 by lambda t as substitute as a function, as a different function like y, then you can go to a certain level and you get an expression, right? You know, e to the power y 5 minus y equal to 0. Sorry, 5 minus y equal to 5 or minus 5 equal to 0. Anyway, so we are not going to, so after that it is not analytically solvable. Think about it, e to the power y 5 minus y minus 5 equal to 0. It is not an analytically solvable algebraic equation. Okay, so you have to do it by numerics or by trial and error, etc. So finally, what this gives is, this results in lambda m, because this is the lambda at which EB lambda is maximum, t is equal to 0.0029 meter Kelvin. And this, my friends, is our second law of black body radiation, known as Wien's law, okay, or Wien's displacement law. I don't know why it is called displacement law. Is it because the peak gets displaced? Maybe. Yeah, when I read in class 11, 12, I also knew it as Wien's displacement law. Later on, when I studied heat transfer, I saw several books referring to it as just Wien's law, some other books referring to as Wien's displacement law. Either way, they're the same. They're used synonymously. And this is what it is. What Wien's law gives us is the value of the wavelength at which the monochromatic emissive power of a surface is maximum at a given temperature. Okay. So if you know the temperature, you know at what wavelength will the emissive power of the black surface be maximum. Now the question is, and this is important, the question is, does it also mean that for a non-black surface, it is going to be the same? So let me throw that question to you. So if I take a non-black surface, will the monochromatic emissive power, the maximum monochromatic emissive power, correspond to the same wavelength? What do you think? Can you be louder?
I think yes, because only the value of E lambda, EB lambda should be scaled up or down by emissivity, but the wavelength should be same.
Okay. Any other thoughts? Any conflicting thoughts? Well, the answer is no. Answer is no. What you said is something that comes to our mind, that E lambda, the emissive power of a real surface, is emissivity times that of the black surface. So why should it change? That's the question, right? What you said is correct only when you can do a gray body approximation, where you're assuming that the emissivity is the same for all wavelengths, but it's not necessary, right? I told you that it is possible to come up with engineered surfaces that the emissivity can be tuned for certain ranges of wavelengths. In such a case, it is not possible. It is not the same, right? So keep that in mind, okay? Only if you're doing a gray body approximation, you can say that the lambda max is the same for a black body and a gray body. But otherwise, that is not necessarily true for all non-black surfaces. Okay. Once we go to some problems, maybe in the next hour itself, we would be able to appreciate it better. Okay. So it's 8:54. Let us take a little early break today, and then come back and do Stefan Boltzmann law, which is the third law. Okay. So see you in 5 minutes at 9 o'clock.